Hello Chem 1ers and welcome to Practice Quiz version 3.1, the annotated experience. We're going to go through and completely work through the solutions of all the questions on the practice quiz. The first question is about solubility, and if each of these would be more soluble in water or oil. So, this first one, part A. Well, if we look at this, it's hydrocarbon city, population this molecule. So this molecule, toluene, consists purely of carbons and hydrogens. Very, very nonpolar organic molecule. So very nonpolar organic molecules are going to be more soluble in a hydrocarbon-based solvent such as oil. Okay, on to the next one. For part B, this molecule is oxalic acid. Oxalic acid is very polar. I mean, look at this. It's got this OH here, quite polar, can hydrogen bond. It's got this OH here, quite polar, can hydrogen bond. We've got these carbonyls here. So there are carbons and hydrogens, but this is a very, very polar molecule. Small polar molecules tend to dissolve much better in water. Finally, we have sodium nitrate, NaNO3. So we have a metal and a bunch of nonmetals. This is a salt. And salts are, for our purposes, can be very soluble in water. So, water for the win here. So again, if you have lots of carbons and hydrogens, and it's just a mostly nonpolar larger molecule, it's going to be more soluble in oil and hydrocarbons. If it's a small polar molecule, or has a lot of polar sites, then it'll be just more soluble in water. And if it's a salt, it'll be more soluble in water. For these next two molecules, notice that in both of these cases that we have these OHs all over the place. We've got and other sundry oxygens as well. So this is a remarkably polar molecule. This is vitamin C. This one's going to be a water-soluble vitamin. Same idea with this next one over here. We've got all these different places where it can hydrogen bond. We've got these electronegative atoms in here and here and here to create dipoles. We've got ourselves another water-soluble molecule. And this is vitamin B6, which is indeed a water-soluble vitamin. Up next, we have this molecule. This next one is vitamin A. So look at this vast degree of hydrocarbon characters. Just so many carbons and hydrogens. Such a largely nonpolar molecule. Sure, we have that one OH alcohol functional group, but other than that, this is hydrocarbon city. So this is going to be a fat-soluble vitamin here. And indeed, that is the case of vitamin A. Up next, let's talk acids and bases. What are the 7 strong acids? All right, let's go through them. The first ones, the first 3 that we're going to look at are just a hydrogen and a halogen. So we have hydrochloric, HCl. We have hydrobromic, HBr. We have the friendliest of them all, hydroiodic, which is just Hi, HI. And in the words of the great poet and philosopher John Bon Jovi, whoa, we are 3/7 of the way there. There are 4 more. They are nitric acid, HNO3, sulfuric acid, H2SO4, chloric acid, HClO3, and then finally perchloric acid, HClO4. These are our 7 strong acids. What of our strong bases? Well, remember, there's 2 things we look for if we're looking for a strong base. It's one of 2 things. So we've got group 1 metals and hydroxide. So group 1 metal and hydroxide, some examples would be potassium hydroxide and sodium hydroxide, KOH and NaOH, respectively. And since the group 1 metal in a salt would have a positive 1 charge, we need 1 hydroxide to counterbalance that. Our other examples are group 2 metal hydroxides. So group 2 metal, with the caveat that it has to be calcium and below on the periodic table. So beryllium and magnesium hydroxide, those ions are too small, they do not form strong bases. But other than that, any group 2 metal hydroxide, calcium below, and remember group 2 metals will have a positive 2 charge in a salt, which means they need 2 OH minuses to counterbalance their charge. So 2 examples of this would be calcium hydroxide, CaOH2, and strontium hydroxide, SrOH2, are group 2 metals, calcium and below, with 2 hydroxides latched on. This next question is about finding the formal charge on each of these atoms. So recall, the formula for formal charge is, it's the number of valence electrons of a given element, aka its main group number, minus the number of non-bonding electrons plus the number of bonds. So let's go through each of these as an example. So for the first one, oxygen is in group 6, and from that we're going to subtract. So it's got 1, 2, 3, 4, 5, 6 non-bonding electrons, and it's got just this one bond here, so 6 plus 1, so it ends up being 6 minus 7, which equals -1. 1 down, 5 to go. For this next one, we're looking at carbon. So carbon is in group 4, and this is going to be, so it's going to be 4 minus number of non-bonding electrons, which there's 2. It's only that one lone pair there. And we can see that there's a triple bond, so there's actually 3 bonds happening here. So 4 minus 5, which is, once again, -1. Not a super common oxidation state for carbon. Very, very reactive carbon. It's a very uncomfortable carbon there. But anyway, so we are good to go. Alright, this next one, oxygen, again, is in group 6, so 6 valence electrons minus. Now in this case, we only have the 2 non-bonding electrons, so 2. And then we've got 1, 2, 3 bonds. So it ends up being 6 minus 5, which is +1 on that oxygen. Okay, now down here we have a nitrogen. Nitrogen is in group 5, so its formal charge will be equal to the 5 valence electrons minus, we've got these 2 lone pairs of electrons, so 4 non-bonding electrons plus, and then we have 2 bonds, 1 and 2. So 4 plus 2, which gives us -1. A lot of -1s here. Okay, up next we have a carbon again. And this carbon is another interesting carbon because, so carbon is in group 4. So we have 4 minus. Notice there are no non-bonding electrons here. So it's going to be 0. There are no lone pairs. And you've got 1, 2, 3 bonds. So 4 minus 0 plus 3, which gives us +1. Very reactive, but it is real and useful in organic synthesis reactions. So then finally we have this last one. Carbon again is group 4, minus there are 0 bonds and, 0 non-bonding electrons and 1, 2, 3, 4 bonds. Which gives us 0 as our formal charge. That's formal charge in a nutshell. This question wants us to draw 2 different ways that phospholipids can interact with each other in an aqueous environment. So we're going to use a cartoon to depict this, and recall that a phospholipid basically has 2 parts to it. It's got the polar head group, represented by the circle. It is hydrophilic. This literally means that it loves water. So this side loves interacting with water molecules. It's charged, it's polar, works really, really well with mingling with water. So that side loves interacting with water. But the hydrocarbon tails, on the other hand, its hydrocarbon tails, represented by these 2 squiggles here. Now remember, they are hydrophobic, which literally means water-fearing. These tails are going to try to get away from the water. So how can we orient these molecules so that the charged polar sides are able to interact with themselves in water, and the hydrophobic ends, the ones that want to get away from water, can only interact with each other? Well, there's a few different motifs that we can see. One possible way that these can align is as follows. They can arrange themselves in a way such that these polar head groups are able to interact with each other and water on this interface over here. But as this would present a problem with the hydrophobic tails, because then they would have to interact with water as well. So what can they do to seal this off? Ta-da! They can form what's called a bilayer. In the bilayer, our hydrophobic ends, these tails, are able to interact with each other, and they minimize their contact with water. So they burrow to the inside of this particular motif, whereas on the outsides we have our hydrophilic polar head groups. Cool. That's one possible way. Here's another. So another way they can do it is as follows. In a micelle. This one didn't turn out as artistically well as I had hoped, but we can kind of still see what's going on here. We have our polar head groups oriented on the outside to minimize their interactions with water, and then we have this basically lipid cord able to burrow away from water. So both of these are examples of how they can interact with each other to maximize their favorable interactions. This next question is about labeling, identifying and labeling the acid-base, conjugate acid, and conjugate base. So a really quick recap of the general idea behind an acid-base reaction. We have an acid. It's got a proton on it. We'll just call this generic acid Ha. And in this corner, we've got a base. We'll call it generic base B. The acid is what loses its proton, so it loses that H+. When it does, since it's losing something with a positive charge, it will go down one informal charge. So this becomes A-, and that is the conjugate base. So the acid, once it loses its H+, becomes the conjugate base, and the base becomes the conjugate acid. Oops, and now that it has one more unit of positive charge, so whatever gives up the hydrogen is the acid. Whatever it becomes in the product side is the conjugate base. Whatever grabs onto the hydrogen, so in this case generic base B grabbed onto a hydrogen, became Hb+. Whatever grabs onto the hydrogen is the base, and it becomes the conjugate acid. This is always true. The charges of acids and bases, they don't have to be neutral. Oftentimes acids are positively charged, oftentimes bases are negatively charged, but we always have this relationship where the acid, when it becomes the conjugate base, since it's getting rid of an H+, it will always go down one in charge. So here it became A-. Likewise, the base, because it is gaining an H+, it will always go up one in its overall charge. So this is the generalization of it. Let's look at the example that we have. For part A, where did the proton go? So it starts here, and then it moves over to here. So whatever lost the proton, that is our acid. That makes the molecule that gained it the base. Cool. Okay, so what of the conjugates? The acid becomes the conjugate base after it loses its proton, and the base becomes the conjugate acid after it gains that nice new proton hat. And so here we have our relationships. Let's move on then to the next one. Okay, for the next one, where is our proton starting? Where is it going? So this proton here ends up being moved over to this molecule here. So that means that the thing that loses the proton, what is that again? That is our acid. The thing that gains the proton, it is our base. The base then, what does it become once it grabs onto the proton? The base becomes the conjugate acid, and the acid becomes, after it loses its proton, the conjugate base. Okay, we've got one more example. Those two involved structures. This last one involves written out molecules. So once again, we're looking for where the hydrogen's going. So between these two molecules, let's see. So this molecule here had two hydrogens, H2CO3 carbonic acid, but then it gave one of them up to become bicarbonate. Okay, so whatever started off with the proton that was moved, that's our acid. Whatever gained the proton, that is our base. Okay, so what are our conjugate acids and conjugate bases here? Our conjugate acid is going to be what the base became. So the base, after it gains its proton hat, becomes the conjugate acid. And then finally that leaves us with our conjugate base. Cool. This question is about the pH of two solutions. And they're both strong acids. That's what we'll be focusing on in Chem 1. So remember that pH is equal to the negative log base 10 of the H plus concentration. And it's used because H plus concentration can typically, in pretty common systems, can range anywhere from 1 times 10 to the negative 14th all the way up to 1 times 10 to 1 molar. And then it can get higher than that. But just for all intents and purposes, we use a pH scale that traditionally goes from 0 to 14, with 7 being the neutral one. We can exceed those numbers. They're not definitive, but this is the most common. So the logarithmic scale gives us an easier way of reporting them. And remember, with strong acids, so whatever the concentration of our strong acid is, when these things dissolve, what do? What makes them strong is that when they dissolve, when they go all out. So they turn completely into H plus and whatever their conjugate base is. This makes our lives easier because whatever the concentration of the strong acid is, be it HCl, HBr, HI, HNO3, HClO3, HClO4, all of them except for H2SO4, which we're not going to do because that one gets convoluted. Whatever the concentration of the acid is, that's also going to be the concentration of our H plus. So our H plus in the solution would be 0.02 molar. Which means to find the pH of this, all we have to do is take the negative log base 10 of 0.02. And this will give us our pH of 1.7. So when we take the log of, in this case, 0.02, it ends up being negative 1.70. And then we just have to change that negative sign, so it becomes positive 1.7. Okay, so we're going to do the same thing again for the next one. So the pH of this nitric acid solution is going to be equal to the negative log base 10 of 0.440, which gives us 0.36. That is quite a concentrated acid. Okay, so for the next problem, we have to arrange the following carboxylic acids in order from weakest to strongest. And remember, a good rule of thumb is look for the number of electronegative atoms on a given carboxylic acid. A little bit of a generalization, but that's what we're going to be rolling with. So, the more electronegative atoms we include, the stronger the acid becomes. So on this first one, choice A, it's got 2 chlorines. And chlorines are pretty electronegative. But what's more electronegative than chlorine? Well, if we look at choice C has 1 chlorine and 1 fluorine. So there's overall a more significant electronegativity disparity in molecule C. But what creates more of an electronegativity disparity and more polarity than, say, 1 chlorine and 1 fluorine? Well, what if we had instead 2 fluorines? Wow! Now it's getting real. But wait a minute. What if instead of that we had not 1, but 2 fluorines, and, just to make it a little bit extra wacky, we have a chlorine here. So the one with the most number of electronegative atoms in it is going to be our, and with the greatest overall electronegativity, is going to create the strongest acid. So if we want to rank these in order from weakest to strongest, we have A is the least, because it only has 2 chlorines, then C with a fluorine and a chlorine, then B, which has 2 fluorines, and then finally D has the most here with 2 fluorines and 1 chlorine. This page is about concentrations, and there's different ways that we can report it. The first way that we're reporting is finding the mass percentage. And so we want to find the mass percentage of, in this particular case, we're looking at sugar in a solution that consists of sugar and water and this molecule here. Okay, so let's have a look-see. So the mass percentage of any given solute is just equal to whatever the mass of the solute is in our solution. So in this case, we have 100 grams of sugar, and then we divide it by the total mass of the solution. So we have a total of 10.6% sugar by mass. Cool. On this next one, we want to find molarity. So I always like to think of what units I'm trying to find first. Remember, molarity, capital M, is equal to the moles of a given solute over the liters of solution. So we need moles of, in this case, HCl, and we need liters of solution. So we're going to need to do conversions for both of these. Let's find the moles first. We have 452 milligrams of HCl. So in order to convert that into moles, first we need to turn it into grams. So remember that in 1 gram of HCl, as well as with anything, there are 1,000 milligrams of that particular substance. And then finally, we want to convert this into the universal currency of chemistry. So looking at our periodic table, for every 1 mole of HCl, hydrogen is about 1 gram per mole. Chlorine is about 35.5 grams per mole, so we add them together, and we get 36.5 grams per mole. So when this is all said and done, we end up getting 0.0124 mole of HCl. Okay, we have half of what we need. We have the mole number. Now we need the liters. That's going to be an easier calculation. So we have the 814 milliliters of aqueous solution. That was just chosen based off of the State College area code. Remember, for every 1 liter, there are 1,000 milliliters, so we just have to divide that number by 1,000, and we end up getting 0.814 liters of solution, which means now we have everything we need to find the molarity. So our molarity is going to equal the moles of HCl, which we found out were 0.0124 mole, divided by the number of liters of solution, which, as we just calculated, by dividing number by 1,000, is 0.814 liters. And when it's all said and done, this ends up equaling 0.015 molar. Okay, and we've got one more calculation here. A scientist wants to make 500 milliliters of a 0.125 molar solution of NaCl. How many grams of NaCl should she add to the water? And we're going to use the same, so we're looking at molarity, so we're going to use the same relationship above. Molarity is equal to moles per liter. So she wants it to be 0.125 molar. Okay, cool. The number of moles, well, that's what we need to solve for. We need to find how many moles it will take. And then we know that it's 500 milliliters of solution, so if we divide that 500 by 1,000, we get 0.5 liters. Okay, so if you know the molarity and you know the number of liters, you can always find the number of moles. So we're going to multiply that 0.5 through, and we get 0.0625 mole of NaCl. Okay, so that's the math, or that's the number of moles, but do we want to know the number of moles? Well, the question's asking how many grams will she need. So we are very, very close. We just need to multiply this by the molar mass. For every 1 mole of NaCl, there are 58.4 grams of NaCl. So upon doing that calculation, we end up getting a grand total of 3.65 grams of sodium chloride. Okay, and then we just have one problem left. A molecule is a decane with an alcohol functional group. Would it be more soluble in water or in oil? This is more or less kind of an application of what we did before, but if we were to draw this molecule, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got our 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't matter where I put the OH, because when push comes to shove, is this more hydrocarbon character or more polar character? Well, look at this massive hydrocarbon here. It's hydrocarbon city. That one OH isn't going to make it very soluble in water. So this one's going to be more soluble in oil because it consists mostly of carbon and hydrogen, and there are very few electronegative atoms to create polarized bonds. And that concludes this video of the practice quiz. Thank you for your continued awesome work, and go and rock the actual quiz.